Okay, now we're going to examine the hexadecimal number system. In this lesson, we have some objectives. First, we want to be able to review the number system and how it is constructed. Next, we want to define a hexadecimal number. Then we want to be able to convert that hexadecimal number to its decimal equivalent. And we want to be able to convert the decimal number to its hexadecimal equivalent. And then we're going to learn how to convert a hexadecimal number straight to binary and not worry about converting it to decimal first. And we will convert the binary number to its hexadecimal equivalent as well. Okay, let's review a number system. A number system contains a system of writing and expressing different quantities within a given set of values. The number system uses a specific set of digits or other symbols to represent each quantity. Each digit or symbol needs to uniquely identify the quantity one from another. A digit is a specific unique shape that is made up that represents a value within that number system. So these are all the digits that are within the decimal number system. A place is a location within the number. The place has a specific identifier and a specific value. So here we have a place identifier of 0, and then as we move to the left, we get 1, 2, 3. We increment by 1. So all the way up to 3 in this particular case, we have a place identifier. Then we have the place value. And we're used to this in the decimal number systems, the ones place, the tens place, the hundreds place, and the thousands place. The base of a number system, every number system has a base. The base determines the quantity or number of digits that are represented within that system. So if we have 10 total digits, 0 through 9, we're dealing with the decimal number system. The 10 total digits represents, in the decimal number system, base 10. The term deci does mean 10, so that's why we use the term decimal to represent the base 10 number system. A place identifier, in this case of 0, if we take the base and we raise it to that place ID, we're going to get the place value. And then if we insert a sample number, we would just multiply down to find the weight of your specific sample number at that specific location. So in this case, we would add across, and the resultant would be 1011. Correctly written, it would be 1011 base 10, so you'd put a little subscript 10 behind it. But since we use the decimal number system so readily, we don't put that subscript 10 behind our numbers because it's just assumed that if there is no subscript, we're using the base 10 or decimal number system. So let's dive into the hexadecimal number system. Hexadecimal or 16, base 16 number system represents 16 different quantities, so it requires 16 digits. So we have the first 9 that we are associated with the decimal number system. But we're going to have to come up with some more digits, and we're actually going to use letters to represent the remaining digits. So for a quantity of 10, we're going to use a letter A, 11B, 12C, 13D. For E, E will represent the quantity of 14, and F will represent the quantity for 15. The prefix hexa actually means 6. Hexadecimal, 6 and 10 together, base 16, is where the hexadecimal name comes from, the 6 plus the 10 out of hexa and decimal. Okay, so we have our place identifiers 0, 1, 2, and 3 here. And then we're going to raise our base to that place identifier to get our specific place values. Our place value is always going to be 1 in this location because any number raised to the 0th power is 1. The next number is going to be whatever the base is, because any number raised to the first power is going to be that specific number. 16 squared is 256, and 16 cubed is 4096. We're going to use that same sample number we've used for the other base presentations, and we're going to multiply down wherever we have quantities. So 1 times 1 is 1, 16 times 1 is 16, 256, we have a 0 at that position, so it nullifies that quantity, and then 4096 times 1 is 4096. Then all we have to do is add across, and we get the resultant 4113 base 10. So therefore, 1011 base 16, or hexadecimal, is going to be 4113 in decimal. Let's look at how we can convert that back. We're just going to use the same number, make sure that we can get back to the number that we started with. Now remember, our procedure is we're going to divide by the base now. So we're going to take our 4113 divided by 16. And if you take 16 times 257, you get 4112, which leaves us a remainder of 1. That'll be the first digit in our hexadecimal number. And then if you remember, 16 squared was 256, so 16 times 16 gives us 256, which is 1 off from our 257, so we'll have a remainder of 1 there as well. And then 16 into itself goes in 1 time with a remainder of 0. Now remember, we have to get 0 over in this location until we're done. So we have to divide 16 into 1, goes in 0 times, 16 times 0 is 0, and then you bring down the 1, and there is our actual hexadecimal number. So 1011 in hexadecimal is 4113 in decimal. Okay, let's look at how we're going to just jump straight to binary from the hexadecimal number and from hexadecimal number to binary. So to represent every digit that we have within the hexadecimal number system, we need 4 specific bits of information. And this is the truth table for 4 bits of information. If you notice, bit 0 here just alternates 0, 1, 0, 1, 0, 1. When you go over to the next column, you just double up what you see in the previous column. So it's 0, 0, 1, 1, 0, 0, 1, 1. You go over to the next column, you're doubling up what you see here to the right of itself. And it's 4 zeros, 4, 1, 4 zeros, 4, 1. And then you repeat that process again. We have 4 zeros here, so we're going to double that up, 8 zeros and 8 ones. That will build us a truth table that will give us every combination in binary for this hexadecimal equivalent. So we know now that we only need 4 bits to represent any quantity that we have within the hexadecimal number system. So if we have a binary number, all we need to do is divide it up into 4s and then convert those into their individual digits. So I'm going to just draw a line right here in half, and I am going to assign place identifiers to each one of those positions, and then we can use, we want to go to the base 2, so we're going to go and raise that base 2 to those place identifier powers, and we're going to get those specific quantities, 1, 2, 4, and 8. So now all we need to do is multiply down from our sample number. So this 1 times the 2 will give us a 2 down here, and the 1 times an 8 will give us an 8. And I just put boxes around the ones that we're going to add together there. And I do the same thing over here. So the 1 times the 2 and the 1 times the 4. So adding those two together, we're going to get 6 here. 4 plus 2 is 6 for that digit, and 8 plus 2 is 10. The only problem is 10 is not a digit in the hexadecimal number system. So we need to look at our little table here. 10 is represented by the letter A. So A is the actual appropriate hexadecimal digit to put there. So our result is 6A in hexadecimal. So therefore, 0, 1, 1, 0, 1, 0, 1, 0 binary equals 6A in hexadecimal. That's how to convert from binary to hexadecimal. Let's look how to go from hexadecimal to binary. So here's my sample number. It's E4, and I'm going to divide this into two specific groupings of 4. I know that it takes 4 binary bits to represent each one of those digits in hexadecimal. So we're going to use what we learned before, and we're going to divide this by the base, that digit by the base. 4 in base 10 is the same quantity as 4 in hexadecimal. So we're using the method that we learned to convert decimal to binary. But in this case, all we have to do is take our 4 in hexadecimal, which is the same thing as 4 in decimal, and use the process that we learned to find out the binary equivalent. So we just take 4, we divide it by 2, and we went through our process, and we got 4 distinct binary digits of 0, 1, 0, 0. Now over here, we don't have a decimal equivalent over here. We're going to have to convert that to a decimal equivalent. So since E isn't a number, we're going to have to look it up in the table here, and E equals 14 decimal. So we're going to use that to use this same process to figure out what our binary digits are over here. So 14 is the value that we want to use, and we're going to take 14 and continually divide it by 2 and drop the remainders down here to get our binary equivalent of this decimal number, which in hexadecimal was represented by the letter E. So that is how we converted from hexadecimal to binary. So the result is 11100100, and 4E represents that number in binary. I hope this helps, and we'll see you in the next video.